In modern France, some of the most powerful machines ever built are designed to never rush. A nuclear reactor exists to hold a reaction back, not to let it run free. This is the paradox of nuclear power. Energy is produced not by releasing force, but by continuously preventing physics from accelerating. Understanding a nuclear reactor begins by understanding what it refuses to allow. This episode examines how pressurized water reactors in France are engineered to slow reactions, not accelerate them. Nuclear fission releases energy when atomic nuclei split, but the process does not settle on its own. Left unchecked, each reaction increases the chance of the next. This is not a problem of strength or output. It is a problem of timing, where reactions naturally try to accelerate faster than control can respond. Chain reactions behave like feedback loops. Each event slightly increases the likelihood and speed of the next, compounding momentum inside the system. The real danger is not how much energy is produced inside the reactor. It is how quickly that energy is released within a confined and unforgiving space. Engineering a nuclear reactor begins with a single decision. The reaction must always be held below what physics would otherwise allow. In France, nuclear power was approached as civil infrastructure, not as an experiment. Reactors were meant to operate quietly, predictably, and for decades. Instead of developing many reactor designs, France chose repetition. One system was refined, replicated, and controlled at a national scale. This decision reduced uncertainty. Known behavior mattered more than theoretical improvements or experimental performance. French reactor programs prioritized systems that could be understood, monitored, and maintained over long periods of time. Control became the guiding principle. Every design choice favored stability, repeatability, and margins over maximum output. At the center of the French reactor design is an ordinary substance used in an extraordinary way. Water is chosen not for power, but for control. Inside a pressurized water reactor, water performs two roles at once. It removes heat while also slowing the particles that sustain the reaction. This slowing effect is essential to control. Without moderation, reactions would accelerate beyond stable and predictable limits. At the same time, water naturally wants to boil as heat rises. Preventing that transition becomes a central constraint shaping the entire system. Extreme pressure is applied, so water stays liquid far beyond its normal boiling point. Stability is achieved by forceful restraint. Efficiency is deliberately sacrificed. The system gives up potential output, so reactions remain slow, predictable, and controllable. The reactor core is often mistaken for the entire machine. In reality, it is only a small part of a much larger system built around it. Most of the reactor's volume exists to manage what the core produces. Distance, structure, and separation are designed features, not empty space. Electricity generation is intentionally separated from the nuclear reaction. Heat is transferred away before energy is ever converted into motion. This separation adds inefficiency. It also adds time, allowing reactions to be observed, adjusted, and restrained before consequences spread. What looks excessive is deliberate. The reactor works because most of it exists to slow, buffer, and absorb what the core releases. To keep water from boiling, pressure becomes the governing force of the reactor. Stability depends on maintaining conditions that resist natural change. Inside a pressurized water reactor, water is held under extreme pressure at all times. This pressure prevents vapor formation even as temperatures rise. Maintaining pressure is not optional in this system. A sudden loss would change how heat moves and how the nuclear reaction is moderated. Engineers design the reactor assuming pressure will be challenged repeatedly. Materials are selected to endure constant stress for decades of operation. Redundancy is layered into every pressure boundary. Backup systems are built to intervene long before boiling conditions can ever appear. Pressure is not applied to extract more energy from the core. It exists to keep reactions slow, predictable, and safely within design limits. Slowing the reaction is an active process, not a passive one. Control systems constantly adjust conditions to keep the reaction below its natural potential. Control rods function as precise braking tools rather than simple switches. They allow engineers to fine-tune the reaction instead of abruptly stopping it. During normal operation, full shutdown is not the objective. Stability is maintained through constant, measured adjustment rather than dramatic intervention. The reaction rate is always kept below what the fuel could physically sustain. Potential energy is deliberately left unused to preserve control margins. Nuclear power operates by refusing to reach its maximum capability. Successful control is defined by restraint, not by output. Nuclear reactors are engineered on the assumption that humans will eventually make mistakes. Safety does not rely on perfect decisions or constant attention. Critical protections are designed to function independently of human action. Physical systems are built to intervene automatically when procedures fail or responses are delayed. Automation does not replace human operators. It exists to limit how far human error can propagate before the system intervenes. Redundancy is built on pessimism. Systems are duplicated, separated, and isolated under the assumption that failures will coincide. Control is maintained by removing reliance on perfect behavior. The reactor remains stable because it expects mistakes, not because it ignores them. The reactor core is often seen as the heart of a nuclear plant. In reality, authority belongs to the containment structures built to govern it. Containment exists to define boundaries. Its purpose is not efficiency, but ensuring that consequences remain confined to one place. Most of the reactor's physical mass is not dedicated to producing power. It exists to manage failure, pressure, and unintended outcomes. If reactions escape their intended limits, containment absorbs the outcome. It is designed to endure scenarios that the core is never meant to experience. In practice, containment is the true machine. The reactor works because everything around it is built to hold consequences back. Maximum output is never the objective of a nuclear reactor. Operation is deliberately kept below what the system could theoretically produce. Running below full potential creates operational margin. That margin absorbs uncertainty in materials, reactions, and the time it takes to respond. Every added margin reduces efficiency by design. Energy that could be produced is intentionally left unused to preserve long-term control. This unused capacity is not waste or error. It functions as a reserve that prevents the system from crossing dangerous thresholds. Nuclear power works because it never chases maximum output. Stability is achieved by staying deliberately below the limits of the system. Even under perfect control, time continues to act on the reactor. Materials slowly change as radiation and heat accumulate year after year. Metal becomes brittle, components fatigue, and tolerances narrow. Aging is expected, measured, and planned for from the beginning. Time cannot be engineered away in a reactor system. Monitoring replaces certainty as gradual change is continuously measured and assessed. Maintenance becomes a permanent process rather than a corrective action. Stability depends on constant attention, not fixed guarantees. A reactor does not fail when it is replaced. Replacement is the final step of a system designed to operate within time's limits. A nuclear reactor cannot be understood as a single machine. It functions as a network of systems that exist to monitor, limit, and correct one another. No component is trusted on its own. Every part is observed, constrained, and balanced by other systems designed to intervene when limits are approached. Power is produced only because these systems remain active at all times. Stability depends on constant coordination rather than isolated performance. The reactor succeeds not through force or speed, but through the continuous cooperation of systems designed to restrain one another. Nuclear power is often imagined as a triumph of force. In practice, it is a triumph of limitation, built around what must never be allowed to happen. Every major decision in a pressurized water reactor reduces speed, output, or efficiency. Control is purchased by accepting less. France did not build its reactors to impress. They were engineered to endure, repeating the same controlled system across an entire nation. Energy becomes usable not when limits are removed, but when failure is slowed enough for systems to respond. The strongest machines are not those that release the most power. They are the ones designed to hold it back.